What we want to do now is to figure out which recursive equation this vector here satisfies. So let's just try to do that. We want to first find an equation that sigma n plus 1 squared satisfies. So the volatility in the n plus first period, what does that satisfy? Well, let's use the recursion for the volatility that we have up here to try and find something useful. So first, note that sigma n plus 1 squared is equal to a0 plus a1 r n squared, because we have n and n minus 1 here. That translates to n plus 1 and n, plus a2 rn minus 1 squared plus b1 sigma n squared plus b2 sigma n minus 1 squared. Can we use this for anything? Well, yes, because what we want to have on our right hand side is something that has to do with Vn minus 1, right? And just note that Vn minus 1 by definition is sigma n squared, sigma n minus 1 squared, and rn minus 1 squared. So what you definitely don't want on your right hand side is the expression for rn squared, and we will therefore try to rewrite that using the definition of the log return in terms of the volatility and the noise variable up here. So rn squared is equal to sigma n squared multiplied by zn squared plus a2 rn minus 1 squared plus b1 sigma n squared plus b2 sigma n minus 1 squared. Now there are a few terms that we can gather here, so let's also do that. Have a0 plus a1 multiplied by zn squared plus b1, and all of those terms are multiplied onto sigma n squared. And the next term that we have is the one with sigma n minus 1 squared, so that has the coefficient b2. And the last term in our Vn minus 1 vector is Rn minus 1 squared, which has the coefficient a2. So we now have an equation for the first coordinate of Vn. Now let's try to figure out equations that govern the volatility in period n, the volatility squared in period n, and the log return squared in period n. So you have sigma n squared. What's that equal to? Well, that is definitely a good question. If we consider what we have in Vn minus 1, then fortunately you can see we also have a sigma n squared here, so we can just write that as equal to sigma n squared. And what you have on this side is Rn squared. What is that then equal to in terms of things that we have on this side? Well, by definition, Rn squared is given as sigma n squared multiplied by Zn squared. And you can see you have sigma n squared here, so that's very nice. So we have the system of equations here. Now we just have to rewrite this system of linear equations into a linear equation written up using matrices. So we have Vn that was given by sigma n plus 1 squared, sigma n squared, Rn squared, and that should be equal to some matrix 3 by 3 matrix A multiplied by sigma n squared, sigma n minus 1 squared, Rn minus 1 squared plus a triple row vector B. And now we just need to figure out what needs to be in these vectors and matrices. Well, first notice that in B, for the two equations down here, there's no constant term. So what we have here is just a 0 and 0. However, for the first equation, we do have a constant term, A0. So A0 goes into the first entry here. Now let us consider the first row of A, which shall denote the coefficients of these three terms in the first equation up here. So the first entry of A should be A1 Zn squared plus B1. And the second entry is B2. And the third entry is A2. And then we can go on to the next row where you see the first entry is just a 1, which is the coefficient on the sigma n squared, and the two others have coefficients 0. And for the last row, the coefficient that you have on sigma n squared is Zn squared, and the two other entries have coefficients 0. Now recall that what we actually want to do in a second is find a stochastic fixed point equation which this vector satisfies. So we will have to try and get rid of the Zn's here because that's not really well defined for n tending to infinity. So we have to figure that one out. So let's just continue to part 2 now, where we want to find a stochastic fixed point equation for the limit of Vn. And what you notice here is that, well, Vn as it is given up here actually has the same distribution as this expression, but where we replace the Zn's by some so-called identical copies. So this is the first step of writing up the stochastic fixed point equation. What we do is you let Z be independent of the entire process Vn. So assume Z is independent of the entire process Vn. Does that actually work? No. That's actually, I'm not really sure if that is the way we really want to go. Well, nah, it works. It works because the only thing that we just need is, the thing is, you know that Zn is independent of sigma n and Zn is independent of Rn minus 1 because Zn has nothing to do with the previous log return. So Zn is independent of sigma n and independent of Rn minus 1. So you can just replace Zn by something that is independent of the entire process Vn, which is a lot stronger it's a lot stronger. It's a much stronger independence condition, and also assume that Z has the same distribution as Zn. So this is what we call a identical copy of Zn. then what we have is that Vn will then have the same distribution as A1 Z squared plus B1, and then B2, A2. You have a 1, and you have a Z squared, and 0, 0, 0, 0. Plus the vector A0, 0, 0. And the second step of finding the stochastic fixed point equation is to let n tend to infinity on both sides. So if you let n tend to infinity on this side, then what you get is v. And when you let n tend to infinity on the other side, well, then you just get the same matrix down here. So you still have the same matrix down here. I don't know why I'm writing it up again, but well, I've already started, so I'll just continue doing that down here. And this vector, which is Vn minus 1, just tends to V as well, since the limit is well defined, because we assume that it exists. And the last constant vector term does not go anywhere either. So we have now written up a stochastic fixed point equation for the limit of Vn. And there might be some multi-dimensional version of the Kestengoldie theorem that can then tell us what the probability is of well, yeah. The thing is the two equations on the bottom aren't actually that interesting, but the first one is really interesting. So maybe we can use the first one. Yes, maybe we can use the first equation to say something about the probability of attaining large log returns. I'm not sure. We can try and interpret this result, but it's easier to just end the exercise here. So the thing that you need to remember about this exercise is that we can use this simple method of replacing something with an identical copy. So because Zn depends on n, we replace it with an identical copy that does not depend on n. And then we move forward just by letting n tend to infinity on both sides.